Olá, pessoal. Bom, primeiro eu quero agradecer, né? Vocês estão aí para assistir mais uma. Tem umas pessoas que estão no mesmo lugar. É interessante. É o hábito, né? É o hábito. Então nós vamos ter a segunda palestra, tá certo? Como eu falei para vocês, nós estamos dando início à comemoração dos 100 anos da mecânica quântica. Vai fazer 100 anos que de Broglie fez a tese dele. Aí depende o país que você está, eles dão um argumento diferente. Aí o outro vai dizer na Áustria que é só daqui 2 anos que o Schrödinger publicou o trabalho dele, aí vai, mas a verdade é que o trabalho de Broglie foi o mais importante. Em julho nós vamos ter aqui um encontro internacional, Laser Physics, onde vai se dedicar 2 dias só à quântica. E estão convidados já, tá bom? Vai vir muita gente de fora, já confirmado, então aí nós vamos fazer a nossa parte. Okay, so thank you for coming. Today we're going to have the second lecture of this series in commemoration to the quantum mechanics. As I told you yesterday, there is always uncertainty related to quantum mechanics, so we didn't know who would speak yesterday, but then we collapsed Bill. So we knew that Bill was yesterday, and we continue our measurement, and we knew that if we wait 24 hours exactly, we're going to meet David. And here is David. David Wineland is a scientist that has many, many contributions. We all recognize that he gave the seminal ideas of cooling atoms and ions, many, many research in ions. He worked with, I think he's the only guy I know that had as a thesis advisor a Nobel Prize. And there was Norman Ramsey that came here 3 times. And as a postdoc, another Nobel Prize, Hans Demmelt. And he's a Nobel Prize himself. So you see, pedigree is important in the Nobel type of stuff. And David worked with the ions mostly of his career after PhD, and he advanced a lot the way to look to ions trapped, the way to put information, cooling the ions, and to use the ions as a special part of quantum bits where you can put information on it. And actually, the work of David is one of the big push for people to believe that we could use the quantum mechanical characteristics, and the main characteristics, to really do computation. And today, he creates a group in NIST in Colorado, in Boulder. And now he moves to help another group in Eugene, in another state. Eugene is a city, Oregon. And but he's always in contact with many, many people. And if there is a guy that can tell us about using single atoms to really do those operations that computer require, and that's David. So we're going to hear Dave. Thank you very much for coming. As I said yesterday, it's not the first time that David come to São Carlos, and it's not the last. We hope he will return many times to give us the news about all the things he's still doing. So thank you very much. Today, he's going to speak about trapping ions, in fact, but quantum computers and raising Schrödinger cats. Cat is a macroscopic object that everybody in quantum mechanics used to demonstrate principles. And originally they used cat, dead and alive, and people keep it cats. But could be dogs, could be cows, elephants too big maybe, but could be anything that's macroscopic. So David, please.
Okay. Well, thanks for the nice introduction, Vanderlei, and thanks for all of you to come to the talk here. I first met Vanderlei when he was a graduate student at MIT, so I've known him for a very long time now, and we've had a good relationship ever since, and have visited each other's labs and so on. So anyway, it's a pleasure to be here. So I'm not going to be able to, you won't learn about quantum computers in this talk. There's just too many details, but hopefully I can give you some impression of what goes on and why it might be interesting. So that's my hope here. Okay, so I'm just going to give a bit of a summary about why we want to use quantum states for computers. And it really brings up a weird situation given by this example of Schrodinger's cat. And I'll say a little bit more about that in a minute. And I'll try to give you some idea how we actually manipulate the quantum states for computers. And I'll come back to this idea of how quantum computers, if we can actually make them, are very, very much like Schrodinger's cat. So one way to talk about superposition, superposition is a very, very strange concept, but one way, a classical analog, which I think gives a pretty good idea of, is an example I'll show here. So if you consider this box in this picture, at sometimes you'll tend to view this face here as being in the foreground, whereas sometimes you'll view this face in the foreground. So you tend to see, it depends on how you play with your eyes, but sometimes you'll see one image or the other. And this is, I think, a good idea of the idea of superposition, that this box up here has the properties of both views that you see in the second picture. And so when you tend to see one image or the other, that's a bit like a quantum measurement. We collapse this quantum state represented by the box up into one situation or the other. So the idea is there's this ambiguity about which state our quantum box is in, but it possesses both properties simultaneously. And then a quantum measurement is just what I said. It's the idea of collapsing one into one image or another. It's like collapsing the quantum states. So some examples of small superpositions. So in our experiments, very much like Bill Phillips, he traps neutral atoms in electric fields from lasers, and we trap charged atoms, atomic ions, in. Actually, we can do it with lasers, but we also do it with lower frequency electric fields. But anyway, you don't need to know much about the details, except a good two-dimensional example is an atom in a trap is like a marble in a bowl. So we can put our atomic marble in this bowl and we can make it go back and forth. But one superposition state we can measure is where the marble is both, at some instance of time, it's on both the left and the right side of the bowl at the same time. And this makes no sense in our ordinary day experience, but this is the world we live in. So anyway, so we can also do this idea of superposition with atomic energy levels. So this little simple diagram on the bottom right here is just to represent the energy difference between two levels, which we'll label as 0 and 1. And we can make a so-called superposition state of those, where it's neither 0 or 1, it's both at the same time, in the sense of the picture above here. So just to give you an idea where some of the power might come from in a quantum computer is that if we compare to a classical bit like we have in our laptops and so on, is that the basic information is carried with a bit, which can be labeled as 0 or 1. But in the quantum world, we can actually make this property where it carries information about both states at the same time. It can be 0 and 1 at the same time. So one interesting property is how the memory scales with this So this is the memory for 1 bit. But if we have a superposition, let's say we're considering 3 bits and 3 quantum bits, first of all, a classical register could store 1 3-bit binary number. But our quantum register, in the superposition sense, can store all 8 possibilities, all 2 to the 3 states at once. So we can make superposition states like this. And these coefficients in the front, they represent, if we measure our quantum register, for example, this state here, for example, will show up with a probability of this amplitude, that we take the square of this probability amplitude, and that gives the probability that when we measure the register, it'll turn out to be this classical 0, 1, 1 state. So the interesting thing about this kind of memory is how it scales. So with 300 qubits, it turns out we can store 2 to the 300 numbers at once. And if we tried to make a classical memory, that's about 10 to the 90th numbers we can store simultaneously. If we tried to make a classical memory that could hold that many numbers, it would take all the matter in the universe. So this is, you can get an idea. This sounds pretty interesting. But of course, we have limitations you'll see here. We can't arbitrarily manipulate. That's at least gives you some impression where the power might come in. So the other thing that's interesting about this is when I'll take what I'm showing in this example here. This is a 3 quantum bit state, and when we measure, just as I explained on the last graph, when we measure this quantum register, it'll turn out to be, for example, 0, 1, 0 with a probability of this coefficient in front squared, the absolute value squared. And so in this example, it represents basically 2 to 3 numbers, or 8 possible states. But for n qubits, then we can store this many numbers simultaneously. And as I said, if this is more than all, in principle, more than all, but if we took all the matter in the universe, we couldn't have a classical memory be that big. The other nice thing is when if we talk about parallel processing, and so when we do an operation, which I'll explain a little bit later, but when we operate on if we make a single gate operation, say flipping one of these bits in this register, it affects all these states at once. And the idea here is, in general, when we make our quantum computer, these coefficients out front, which are again the probability if we measure measuring the particular numbers, are these coefficients the absolute value squared. So but when the idea, one of the potential advantages is that I guess I already said this on the first case, but anyway, so the idea though is if we flip one of these bits, in general, all these coefficients are going to be different. So the idea is if we flip 1 bit, it's going to change all these the states of what I show here. But in general, all these coefficients are different. So basically, you're changing all 2 to the n coefficients at the same time. So in some sense, that gives you an idea of how we can do massive parallel processing with these. Anyway, so we have our measurement rule. Again, I'll just state it again. When we measure this register, we're going to get, say, 0, 1, 0 with this coefficient out front, the amplitude of that squared. So that's the limit we have to live with. Anyway, so jumping ahead now, so in the mid-90s, Peter Shor, who is a computer theorist, or he's really a math, he's more general than computer theory. But anyway, he came up with an algorithm that might be able to do some interesting things. And in particular, he made. Let me back up here a minute. So he made an algorithm which would efficiently factorize large numbers, and maybe many of you know, you students are much better at computers than I am, but basically almost all secure encryption systems derive their security from the inability to factorize large numbers. So if Peter Shor's algorithm could be implemented, and then it compromises basically certainly the most popular forms of data encryption. So anyway, this, not surprisingly, this got the government interested in the U.S. The national security is of course in charge of all secret encryption, and so they had to be in this game, because in principle it would compromise. Well, the most popular, again, many of you students, they know the most popular encryption method is called RSA, the initials being after the 3 Israeli scientists who invented this algorithm, but it derives its security from the inability to factorize large numbers. So their code would be compromised if we could do that, if we could crack the code. So anyway, one thing the operations we can talk about are, let's just compare to the classical case. In a classical computer, it may not be the most efficient way to do computations, but you can do universal computation, do any computation with just 2 operations, and one is just a bit flip, and the other is a so-called 2-bit AND gate, which has this truth table here. And there's other forms that will work, but they're classical gates. But again, just to stress, in principle, you could do any computation that you can do on your computers with just a combination of these 2 gates. There's an analog in the quantum world. Oops, let me go back. Didn't want to do that yet. Sorry. Anyway, so the analog in the quantum world, again, we instead of talking about a bit flip, we can talk what we call about a rotation. And this is where we start to get pictures about quantum mechanics, but the idea is we can make a transformation where the 0 is not just doesn't go to 0 to go to 1, but it can be a linear superposition given by these expressions here. And those may not make any physical sense, but one thing we can think about in quantum mechanics, if we talk about a spin 1/2 particle in a magnetic field, it can have 2 states. It'd be in the up state or the down state. But we can also make superposition states where it's in a combination of both the 0 and the 1 state at the same time. And it turns out that, when we picture this, it's like taking a spin 1/2 particle and not rotating it completely to make a NOT gate, but to only rotate it part way. And then it'll have a probability of being in both 0, 1, and this theta in this expression corresponds to the theta between the vertical axis and the direction that we rotate the spin into. So we can actually, it's fairly easy for us to make the quantum bits this way. Manipulating them is another story, of course. So anyway, just to give an idea that if we have if this is our logic gate, and you'll see in this picture here, all we do is that the values of the magnitudes of the states don't change, but in this so-called phase gate, this 1, 1 state will get a minus sign in front of it. We call that a phase gate. Because -1 is equal to e to the I pi, in this case a pi phase. Anyway, so this is the kind of thing we think about. And the interesting part of this is it comes back in a way. It generates the idea of Schrodinger's cat. That is, if we can make with this simple gate operation, if we have an equal superposition of 2 qubits, then we can, if we apply this operator here, we can come up with a superposition that picks up this minus sign. And now we can't, for the initial case, we can actually we can represent the numbers of products of 2 quantum states. But when we measure this, when we implement this quantum gate down here, we realize entanglement. In that case, we can no longer represent the 1 state as independent of the other. They're combined, so we have to take care of both possible configurations to get this. And this entanglement is key, and it may not be obvious, and that time I'll have to explain here, but it's one of the key features of quantum computing. So anyway, whoops, let me make sure I didn't go too far. Okay. So actually, some of the early ideas about quantum information actually don't involve the things I'm going to talk about here, or what I briefly tried to introduce. But there were some famous people, Richard Feynman, David Deutsch, and Paul Benioff. These last two guys were famous computer theorists. But anyway, they were initially thinking about using quantum states, but not in the sense that we're going to talk about here. They would just talk about, say, electron spins, and they would use an electron spin being up parallel to a magnetic field or the opposite state, but it would be just like a classical bit. Nevertheless, it was quantum, and so in some sense they were the first people to think about using quantum states for computing. But it was Peter Shor then who came along with this efficient factoring algorithm, which is much more certainly much more involved than the ideas of just using quantum states to represent classical bits. And I guess I had already mentioned that the reason this got immediate attention was that again it would be able to realize an algorithm which would factorize large numbers, which is where the security of one of the most common systems, RSA, is based on. So just to say a little bit more. So we're gonna need a lot of bits in our system. But just to give you an approximate idea, I'll show the case for 3 quantum bits. And in general, the idea of any computation is we'll have some register that can hold all the numbers we want to use in our computation, and we plug that into. These can be in classical bits, but then we represent those by spins or 2-level systems and atom, and we apply basically just a series of these 2-qubit gates that I showed on the last view graph. Oops, maybe I'm getting too far away. Anyway, that was the basic gate that I showed before, and the idea is this is just represents a series of operations that we repeat one after the other, and the operations with 2 indices, or those are the quantum gate between 2 quantum bits I tried to describe, and then the other one is just a rotation, that other single bit operation that I described. So actually, the way this works is, let me back a little bit again. The idea is that we have in the register, in the input register, it actually is just like a classical memory. But then we can convert that classical memory into quantum bits, and then we do a series of operations, and it can just be the 2 that I described on different combinations of the qubits. And anyway, but in some sense, all these coefficients of the quantum state we say are phase coherent, and the simplest, or at least a simple example of how you get the idea how this works is that I think many of you in our first maybe classes, even in grade school, we see how if we have in this example here, we're looking down on a shallow tray that holds water. And this experiment that I had seen as a kid, and it's done in many places, is you have from the left you have a wave coming, a water wave coming in, and most of it will be reflected by this barrier, but a little bit will be transmitted by these openings, these slits. And what you see on the right side, as the part that propagates through, you can see these interferences where it appears the waves go away, and in other cases where they're enhanced. And this is very similar to what happens in our quantum bits, is that these wave amplitudes can interfere. So in some cases, they cause the information to disappear, and here they amplify it. So. Anyway, so it's of course much more complicated than that, but to exercise his algorithm. But anyway, so the idea again is we plug into this quantum computer first of all a classical number, but then we convert that to these quantum states, and then we apply these series of operations, and then finally, after this interference represented by the water waves, we measure the amplitudes of all the bits coming out. And from what I've said here, you're not going to get an idea how it really works, but this is the underlying principle that we rely on, this interference between these quantum states. And just to give you an idea, I showed you two simple gate operations, but anyway, to be interesting, for example, to factorize a 150-digit decimal number using this method, which would even these days the secure numbers have to be above 150 digits, so they're not very viable. But anyway, with using these quantum operations, it would take about 10 to the 9th of the quantum operations that I showed, so a huge number. And so you can see we have to try to make those operations very precise. So anyway, now I'm going to switch to Schrodinger's cat, and this may seem to be a big deviation, but it actually involves the same ideas of what Peter Shor was telling us about how we might be able to make a quantum computer. Anyway, for those, I think many of the physics students know this example that Schrodinger came up with in 1934. So Erwin Schrodinger was one of the inventors of quantum mechanics. And he and other people like Einstein, they were dissatisfied with the consequences, because if they followed the logical consequences based on the ideas I just explained, you come up with this weird situation that Schrodinger came up with, and that is the idea. The way they explained the weirdness was suppose you had a system where you had a sealed box where these things inside the box wouldn't interfere with be caused to be disturbed by outside influences. And suppose we have one radioactive particle and some mechanism, if the particle decays, it releases poison and kills the cat. And anyway, this sort of macabre example was what Schrodinger came with. But anyway, what quantum mechanics tells you fundamentally is that after one half-life of the particle, in other words, after a time where the radioactive particle has a 50% chance of probability, all you can say before you measure the system is that it's in what we call an entangled state. The entangled part is that it's in a superposition of the cat being both dead and alive, but that is correlated with whether the radioactive particle has not decayed or whether it has decayed. And that's the entanglement part, where the two systems are coupled together. Anyway, so I think because of this was the natural conclusion that people like Schrodinger and Einstein, the founders of, that really developed quantum mechanics, they were bothered by this consequence. And so they decided there must be something wrong with quantum mechanics. And it turns out there's not. And in fact, the Nobel Prizes from 2 years ago were given, which showed this property of entanglement, where it wasn't a cat and a radioactive particle, but the ideas was just the same. And the interesting part of that is that they could separate the two systems, the two possibilities, by a very large distance. So, and one of the features was interesting. If they measure one state of it's over here, the cat being correlated with alive, and the particle not decayed, with the other one not the particle decayed and the cat dead. There's no way, in principle, we fundamentally hold the idea that there's no way we can communicate faster than the speed of light. So the reason they didn't like this idea was that it required, superluminal communication. Well, it turns out it's not the case. The result is what I said, you do get a result which looks like superluminal communication, but these Nobel Prizes from a couple of years ago made systems like the cat and the radioactive particle much more polite to cats and so on. But anyway, they could create states like that, and they could show that there was this correlation that somehow went faster than the speed of light. In other words, if they saw, in the cat example, if they saw one state, and another state separated by some very large distance, they would be correlated, even though there was no way for them to communicate. Anyway, so that's one of the the interesting consequences of all this. But anyway, so this is a thought experiments, and these thought experiments are now our world. We have to believe in these weird things, these weird correlations that might come about, and this is the idea. This is what Peter Shor tries to exploit in his factoring algorithm. So anyway, so we first of all, I don't have a very interesting punchline. We're very far away from implementing something like Peter Shor's algorithm, and it's just because we don't have good enough control over the systems. But I think we're optimistic that we'll eventually get there. But anyway, I'm gonna try to give you some ideas of where we hope and think we're headed. So anyway, this idea of first of all, we need precise control of the environment, and in other words, to isolate our qubits from the environment. Actually, examples that we're familiar with from earlier days is to make atomic clocks based on transitions in atoms. We need very good isolation, and we of course need them for our quantum computers. And these days now, there's many people and groups involved worldwide, and there's a lot of commercial interests, you can imagine. So there's a lot. I'll say a little bit about that in a while. But so anyway, I'm going to give you some idea at the very small scale of what kind of things we can do. So this is just one example, and I'm going to give a talk on atomic clocks tomorrow, and I'm going to use this example of our mercury ion optical qubit. Anyway, we can label these atomic states, which are separated by an optical energy. We can in this case we label them with up arrow and down arrow. Again, in analogy with an electron being pointing up or against the magnetic field. Anyway, these were the experiments done, some early experiments done at NIST, and my close colleague and friend there, Jim Berquist, was a laser expert, and we actually used an ultraviolet transition that, so way beyond what a visible transition. But anyway, it had a separation that was in the ultraviolet energy that corresponded to ultraviolet radiation. Anyway, just to get some of the basic ideas, we put our mercury ion inside this structure here, and I won't try to go into all the details, but this trap works by this system of electrodes that creates a combination of static and oscillating electric fields, and it turns out those can form a potential. These oscillating electric fields are actually, they work on the same principle as the laser trapping that Vanderlei and his colleagues and Bill Phillips use, except it can be at a very low frequency, but it's the same basic idea as the optical traps. Anyway, so we can make this three-dimensional trap, and what we can do is, for example, to play a little bit with our qubit, I've used these atomic notations, but again, we'll just label them with down and up arrows like the electron spin. Anyway, if we start the atom in the ground state, we can apply a laser that connects those two levels for a short amount of time, and in fact, in that case, then we can make a superposition where, again, these coefficients in front, the amplitude squared represent the probability. If we measure the state, it'll turn out to be in the levels that we've labeled down arrow and up arrow. Anyway, this radiation that we do these operations at a very short wavelength. It's in the ultraviolet, which you can't see, but that doesn't really change anything about the physics. We have another way to detect, though, another way we measure our qubits then, is there's another laser we can use. It's even a shorter wavelength, but it turns out this one, I should have said first, the upper level of our qubit transition, in principle, it can last very long time, much longer than the time of operations we're trying to invoke with our hopeful quantum, with our quantum computer. But we can use another way to measure these transitions. There's another transition, and this is true of almost all atoms, but I'll give the mercury example here. There's another transition, which is at an even shorter wavelength. But the idea here is that if we shine a laser beam on our qubit ion, if we measure our superposition state and the ion turns out to be in the lower state, then we can scatter a lot of light off this transition, and we can pick up a little bit of that with a photomultiplier, which is a small fraction, allows us to uniformly or unanimously determine when we had the qubit to be in the spin down state. Oops. Okay, but on the other hand, if we try to make the qubit transition, and in fact the atom is projected to be in the upper state, then when we turn on this second laser, we don't see interscattering. And we can essentially tell with 100% with this method whether which state the atom, the ion is measured to be in. So and this just gives a demonstration of that. So in this simple experiment, we turned on both lasers at the same time, and you can see this time here is a little less than the second overall, but we can, this atom will, as we're applying this later, we apply this later, but sometimes the atom will be projected up into this state, and then we see this scattering from here, but then other times it's in the ground state, and then we can see a lot of scattering. So that's what the switching you see here. But one of the things hopefully you can see here is that we get quite a good differential between seeing the scattered light or no scattered light. So essentially we can tell with 100% efficiency which state the atom, our qubit, is in when we measure it. Okay, well, I said a little bit about Peter Shor, and I'll say a little bit more about the history at least from iron trappers like myself. And one interesting thing was that, so Peter Shor came out with his algorithm in 1994, and when it hit the airwaves, I mean, there was a lot of excitement about that. But anyway, I think most atomic physicists, certainly myself, we didn't know anything about his algorithm. But anyway, we invited another theorist who's an expert on quantum communications to present the basic ideas of Shor's algorithm at this international conference on atomic physics. And anyway, so he explained some of the basic ideas I've said to you. So anyway, in the audience of this meeting, there were two of our from the atomic physics side. There were two of our favorite atomic theorists in the audience, Ignacio Serret and Peter Zoller, who were both at Innsbruck at that time. And one of their, I'd say, one of their great attributes is they're, first of all, technically very good theorists, but they also take close attention to what experiments could do. So they knew what we could do. They were keeping up on the literature. And in fact, in Innsbruck, one of our colleagues was there. We're playing similar games. And so, but what was interesting, when they heard this talk about the basic ideas of quantum computer, within literally 2 weeks, they came up with an idea how we could do this with ions. And so they were nice enough to send a preprint of their paper to us. And it turns out we had been, when I say we, my main colleague at that time was Chris Monroe. Anyway, we had been playing with, not mercury ions, we were playing with some other beryllium ions in that case, but the ideas were basically what I presented for mercury ions. But anyway, they came up with this idea how you could, in general, how you could carry out the basic operations. So I'll try to just give you a rough idea how it works. So I'm going to, again, in this case, wasn't mercury ions, but it was magnesium and beryllium that we played with. But anyway, you have the same idea. We're going to label these two states, in the internal states in the ion with these arrows. But we're also going to now consider the motion of the ions in the trap. And so if we have n ions, in general, there's 3 n modes. In each dimension, there's a number of oscillation motion modes that correspond to the number of ions. In the simple case, if you just consider two ions and you consider the horizontal direction, so suppose they're separated by some distance, there's 2 motional modes we talk about. It's just like molecules, but there's 2 modes. One is where the particles are oscillating in opposition, and the other one is when they're oscillating in the external will together. And it's those are the kind of modes. With 5, there's 5 modes total, but they have the same property that they're separable into different configurations. Anyway, so the idea of their scheme was the following: is that you would suppose you could freeze out the motion with laser cooling. Then you would, if you wanted to carry out an operation by corresponding to this quantum gate, the idea was, in general, say midstream of a calculation, all these ions are going to be in superposition states. They may be entangled superpositions. It doesn't so matter for what we're talking about here, but the basic idea of their scheme was, if, say, for one of the ions, we would map the internal state onto the ground and first excited state of motion, the mode that we had done the laser cooling to the ground state. So the idea then of their scheme is the following: is that suppose you can do laser cooling, and let's just consider the horizontal modes as ones that we're going to use. So, but with laser cooling, we can freeze out the motion, so all the 5 modes of motion in this case are exactly in the quantum ground state. So then what the idea of their scheme was, in general, the qubits, say mid-operation, are going to be in superposition states. But what we could do is we can take a laser and we can map the superposition state of this ion onto a superposition state, which is the motion of the ground and first excited state of some particular mode. And for the simplicity, I'll just take the so-called center mass, where they're oscillating together. Anyway, so then from there, the idea is if we could then do a quantum gate, it's similar to the ones I've described previously. If we can do a quantum gate between this internal state qubit and the qubit that we've made by mapping the first qubit into a superposition state, then effectively we've done a quantum gate between this qubit and this qubit through this mapping operation. And then when we do the quantum gate between qubits performed by the internal state and the motion for that particular mode, then we effectively done the quantum gate. And then to get back to where we started, the idea is we take this state and then map it back into the superposition that the ion was originally in. So anyway, it's steps like that we can use to, and we can of course do it with different sets of ions and carry on that way. So anyway, just again to give you the idea so for our optical qubit, just like the case I mentioned before, we're going to have the qubit states themselves are going to be separated by optical energy, and these motion states are very low energy compared to the optical energies, about typically in terms of frequency about 1 to 10 megahertz in the experiments we were doing. But nevertheless, we can do this mapping operation. We can drive a transition that takes this upper optical state and then maps it down into the motion, and now we've converted the motion. The superposition was of this state and this state into this superposition of those 2 states. And then for the second operation, I mentioned that we first mapped this qubit state into the motion, and then now we're going to focus on this state down here. And so in general, after the first mapping operation, this qubit is going to be a combination of 4 states. It's going to be a combination of the internal states and the motionals, the 2 possibilities for the motional states. And the way we can do a quantum logic gate, it turns out, is we can, it won't be quite the same as what I said before, but what we can do is we can take this upper state here. There's another level in the ion we can map to and then map back out again. And it turns out when we do this mapping back and forth, we call that a 2 pi rotation. But the key part is that this operation it takes this state, this particular state here, and puts a minus sign, this pi phase shift on this state. And that's the key operation we need to do these quantum logic operations for Peter Shor algorithm. So that's, anyway, so we had the basic ingredients, and then of course the trick now is to scale up. And so anyway, and I should say our colleagues in Innsbruck, the experimentalists there, they carried out the complete scheme. We had done this first basic logic operation, but they were able to carry out the complete scheme before for 2 ions. And then, of course, we and the Innsbruck experimentalists were trying to go farther, as well as many other groups by that time. Anyway, so the one slight drawback of everything that Sirac Gonzalez said was fine. It turns out that to get very precise control is that we need very precise mapping in these steps, and the kind of errors we're going to allow in the system is where we make only a 100% error in the operations I talked about. And it's difficult to carry these laser operations out the way I've described them at error of 0.01%. So I'm going to, this gets a little heavy maybe, but hopefully I could pull the physicists along here. So anyway, not long after that, so there was another first theorist that came up with a basic ideal I'll try to describe here, Molmer and Sorensen, and there were variants on this that I list there as well. But the first 2 authors I listed I showed were there. So anyway, the idea is now so in general for a motion, if we can rep a motional state, let's say we have an atom oscillating, then what happens is, in time what happens is that if this blob represents our ion, and in general what happens is that as the ion oscillates, it exchanges between position and momentum in this 2-dimensional diagram where I put position and momentum. And what happens is the oscillation going back and forth is represented in terms of position and momentum as a circular state that goes around at the frequency of oscillation. Anyway, for small, it turns out for small dipper, if we do small displacements of this wave packet that represents our motion state, well, this is a little bit of heavy, maybe too heavy math for here, but anyway, we can actually make small displacement of this, and we can concatenate those displacements so that we can make a circle in phase space. And it turns out if we make a circle in phase space and bring the state exactly back on itself, it turns out we pick up a minus sign, and this is the minus sign that I was showing you before. So, and it turns out the actual sign we pick up is the phase we pick up is in portion of the enclosed area, and we adjust the phase so this e to the I phi is -1, and that's what we want for logic gates. So anyway, we can actually make these logic gates between the states by mapping through the motion in the way I've described here. So anyway, and in this second, this more fancier version of how we do the gates, the way we can apply forces to the ions is what we do is we take 2 laser beams that are at slightly different frequency. So these optical beams that interact with, they aren't tuned exactly to the optical resonance, but off the resonance a little bit. And anyway, we can make a standing wave. If the 2 frequencies of these lasers are the same, what we do is we make a polarization or intensity gradient. Just think about the intensity gradient. But what happens, these waves that come in from 2 different directions, they interfere, so in some cases the wave amplitudes go to 0, in some cases it reaches the maximum intensity. But the idea of these gates is we'd tune the lasers a little bit, and then we'd sweep these forces, these optical forces across the ion. So I just show 1 ion here, but the idea then is that we would displace it in phase space by implementing this standing wave, this sweeping standing wave for a certain amount of time. And we would pick up a phase which was proportional to the enclosed area in phase space, and we would adjust that so it would give the -1 sign. Anyway, so that's basically what we did, and just to go a little bit beyond that, so in the case of two ions, we have two gates that we might consider. So what I show here is suppose the states of these two ions are different. If we force the ions, then it turns out that this ion is going to be, it doesn't look like it in this picture because it interacts differently with the slope of these waves. It'll be pushed to the left, and the other one will be pushed to the right, and it's this difference which then gives us this force which pushes the ions in phase space around a circle. And for the other case, where the two forces are in phase, nothing happens. It doesn't push the oscillation for this particular oscillation mode. So anyway, the nice thing about this scheme is it doesn't depend on the initial state of the wave function. But we need to ensure the idea that the amplitude of the excitation, the motion, turns out it has to be much smaller than the wavelength difference between these standing waves. And the reason for that is that if we make the slopes of those interference patterns too steep, then it brings in higher order effects that cause errors in the gate. Anyway, I won't go through the details of that. Anyway, the simple picture is that we could do this on making gates on the states that are for the states where we describe, like electron spin along the z direction being up or down. We can do it for forces in the other directions as well. Anyway, I won't. I know it's getting a little heavy here, but anyway, so some of the first, this was the Innsbruck group, and we were sort of running neck and neck. I won't explain the details here, but the key thing is they could reach a fidelity in their 2-qubit logic gates of this. The precision was about 0.993. And there were other kind of gates based on, in their case, it was optical states, but we were using so-called hyperfine states of the ions. But anyway, a lot of details there. But anyway, so this was the kind of the situation in the around 2015, so on. And anyway, so we were able to get to, of logic gate fidelities of these 2-qubit gates of about 99% in these three experiments. This was our experiment. This was the experiment in Innsbruck, and there was another experiment in Oxford. It turns out, a lot of details that go into this, but we want to get even higher precision. To really have a go at factoring, we want to get it to at least 4 nines. So anyway, what was kind of funny after we reported these results together essentially at the same time, and so this was published in Phys Rev Letters, and one thing was interesting. The authors usually like to single out some articles in each edition, and they singled out our two papers. And what was nice is they gave us another digit of precision than we really had, so we were happy to see that. But anybody that read the papers knew what was going on. Man, it was just kind of funny. So anyway, it turns out we can do this. I've described how this works on just 2 ions. And Chris Monroe, my colleague, where we did the first experiments, he eventually he went to the University of Maryland, where he did the experiments I'll describe here. So basically, they worked with long strings, and for each, these strings of n ions long, they could do, they could make states or n component states. And there were also n different modes of motion. But anyway, they could, just qualitative, they could couple the 2 modes of motion by focusing laser beams. So in other words, the long and short of it was they could do, by focusing their laser beams on one particular a pair of ions, they could do the logic gates between this group and this group that were, although that doesn't look like in this picture, but it was all based on modes that utilized all the ions. So they basically were doing these logic gates between the two ions that were selected with the laser beams. Anyway, this is a bit more details. We could adjust the phases of these oscillations to prepare states of this form here. And the other thing about the nice thing about this situation with ions is that Chris Monroe actually later was one of the founders of a company that was trying to develop quantum computers based on these ideas. But one thing they emphasized about the ions was that, let me back up here, was that basically it would, you could focus on any pair of ions in the string, and what that means in the laser or the quantum computing, jargon is it means, you can connect to any two pair of the ions in the string, and call that full connectivity. So what about scaling up? And so I showed you, one for a very simple kind of trap. One other kind of trap we and others were developing were 2D arrays. And so the basic idea here is that this is a set of electrodes. Here they look like they're suspended by some magic process. But anyway, these are the electrodes of the trap, and we could make regions where we would have string of ions and as memory units, and the other thing is that we would divide these electrodes up so we could apply potential these yellow electrodes so we could separate off one ion and then move it out, and then maybe move it somewhere else to interact with another ion that we could make our quantum logic gate. And then, so by this process of shuttling ions around, we could scale up in these systems. Anyway, and the other thing we had to have, because when we move the ions around, we could do it pretty gently, but eventually they would pick up energy. So at each step where we would pick off an ion and move it together with another ion to do a logic gate, we had to cool the motion back to the ground state. So in that case, we would actually have another ion. In our experiments, the quantum bit ions were beryllium, and the other one was a magnesium ion. But the idea is we'd put a magnesium ion next to our qubit ions, and the Coulomb interaction between those three ions was strong enough that if we cooled the magnesium ion, it would cool the qubit ions back down to the ground state. So this is part of the process we have to go through. Anyway, so just to fast forward a little bit. So we made some traps based on this idea here. One of the first ideas we had was we started doing microfabrication techniques. And so this is two sets of electrodes we'd sandwiched together. And in this case, it was only two zones between this area and this area here. And we could, by applying electric potentials on these separate electrodes, we could move ions between these two zones. And so that was kind of the first crude step. And now we and others have made memories, traps that have many memory zones where we can move ions all around. Let's see. One thing I just give a little bit more on the traps is that so this is the basic configuration of our 4-rod trap, and we can actually, where we did those first demonstrations I just mentioned now, but we can actually, rather than having the electrodes in 3 dimensions, we can distort the electrodes. From this little cartoon was supposed to show that we can actually distort the electrodes, put them in a plane. And the nice thing about that is it's much easier to fabricate these planar structures. And this gives one example where it doesn't look, you have to think carefully, but anyway, each one of these little tiny squares is a trapping zone based on the electrodes surrounding it. And there's I don't want to forget, about 100 zones here. But the idea is we could, in these planar structures, we could apply potentially these electrodes, and we could actually move two ions anywhere in this location, and we had little side tracks here. Anyway, we called this racetrack for the obvious reason. But anyway, we could demonstrate this idea of scaling up to large numbers. The other alternative scheme, which Chris Monroe's group pioneered, was to, rather than moving the ions around, one way you can connect two ions in remote places, it turns out you can entangle the motion with the ion in a similar way I described about, and then you stick any radiation that you excite from your 2-qubit, in this case your terbium. You can pick that radiation up, you can confine it in an interferometer based on quantum principles. Anyway, the net result is you can entangle the two ions in these separate locations by the detections you make in this interferometer. So these are two ideas of how to scale up. And I think that's just what I said, but okay. So the other thing I've talked mainly about the application to quantum factoring, but what's come up, certainly, I think for physicists, the more interesting thing is that we can simulate Hamiltonians, physical systems that are very hard to simulate quantum mechanically. And one is called the transverse Ising model. It's magnetic coupling between an array of qubits. And the idea there is we can convert the mapping operations I've talked about before to simulate these interesting condensed matter systems. And so these are two examples here in our group. John Bollinger was the one that using similar experiments, but in this case it was a 2D. It was like a pancake of ions, but anyway, he could show how you could connect the difference ion in this pancake simple. Anyway, so it's by now a pretty big group of people around the world. I confess that this slide is a few years old now, but there's actually Rainer Blatt, one of our colleagues in Innsbruck. He keeps on his website, he keeps a tab on who's working on what. And now it turns out there's over 100 groups just working on trapped ions, trying to make quantum processors. And I show a few of the groups there. But there's many other physical platforms. Certainly people are working with neutral atoms, like what Vanderlei and Bill Phillips work on. And one of the more popular ones is to use superconducting Josephson junctions to make arrays of qubits based on Josephson junctions. And that's probably the second most, maybe an equal amount of work is being focused on these Josephson junctions. And there's other ones too. I don't have time to describe her. But anyway, so there's a lot of interest in this now. And just to say a little bit about superconducting qubits. Again, this few graphs a little bit out of date, a few years out. But anyway, I listed the groups working on superconducting qubits. And the way they connect their qubits is not so much different than what we were talking about. In that case, rather than using the motion of our ions that couple together, is they would couple them up. Well, it's actually via microwave signals, but they could effectively realize the coupling we could realize with a Coulomb interaction. Let me see if anyway, this just gives some more examples of these. So this one here was kind of interesting to us. So this one was just a two-zone gate for so-called two-dimensional electron gas. So the idea is you have a planar surface that can hold electrons. And one thing that's interesting about this is it looks very much in a way like our ion traps. And so, but anyway, a lot of work has been done on that and other versions of condensed matter systems. So what about the future? And so anyway, we more and better to really make progress on this. We have to be able to scale up much higher than the ways I've described, or maybe using the ways I've described, but we have to get much higher accuracies. So I mentioned that we could get to 10 to minus 3 errors in our 2-qubit gates. Actually, we're down now to 10 to minus 4, but we want even more. Anyway, the other thing is just all sorts of weird problems we have in the ion case. What we notice is if we cool our ions down, we have to worry about ambient electric fields that could act on the charge of the ions and heat the motion up, which would compromise the accuracy gate. And the disappointing part was we saw much higher electric fields than we would anticipate from the thermal electric fields. And so what we've, with help of others, we learned is that the charge can move around on the electrodes and cause heat. Electric fields are much higher than the thermal electric fields. So anyway, we're working on that in part, mostly just by cooling things down even farther. The other thing I haven't talked about at all, but I've given you the basic idea of how we could scale this up. But in fact, errors are always going to creep in somewhere, and we have to be able to correct for these errors. And that is another whole step of complication how we do this, a quantum system. So the picture gets much more complicated. But to do anything like factoring an interesting number for communication, we have to be able to correct for errors that they're coming in from these anomalous effects. So anyway, what about the factoring machine? It's still a long way away. RSA doesn't need to worry at this point, but anyway, the other thing is that I think we're using these basic ideas to do spectroscopy. I'll say a little bit about this tomorrow when I talk about atomic clocks. But there's several companies now, and this is a list which is incomplete. It features both trapped ion companies and superconducting qubit companies. And now there's at least 4 trapped ion quantum computing companies that you can find on the web. There's a lot of commercial interest in this now. Probably, as I say, I think that if we make a quantum computer that it would compromise RSA, the standard encryption scheme that's used now. But Peter Shor, even with talking to him with the last 6 months, he said now the classical cryptographers are coming up with schemes that, as far as he knows, a quantum computer couldn't crack. So that initial application that got things going may become obsolete. But I think that's more interesting anyway for us physicists is to simulate these other quantum systems that we can do with a quantum computer. So anyway, I forget what I was going to say about here. Anyway. So, what I was going to say here is that, anyway, we can make in principle, we can, on a baby scale, using our separated zones, we can make a quantum state where it's I've changed the notation to 0 and 1 instead of spin up and spin down. But anyway, we can correlate a single one of our ions with another group of ions to make an entangled state, where this is, it can be a large enough number of ions that you can view it as more of a macroscopic magnetization. And so, we speculate that if we could reach a situation like this is pretty much like the situation of Schrodinger's cat. That is, where we're entangling a microscopic particle, in our case, one ion. In Schrodinger's example, it was a radioactive particle. But then we can entangle that with a more macroscopic object. In Schrodinger's case, of course, it was the cat. In our case, a little less spectacular, but we could maybe measure the macroscopic magnetization, say, with a classical meter, like a compass or something like that. Anyway, so this is something that we're aiming at for fun, anyway. And with that, I'll switch. So this was I was at NIST in Boulder from 1975 to 2018, and I don't know, for various family reasons, I moved from NIST. But this was our group in 2018, where most of the work I've talked about here was reported. And so the main thing I want to say was the important part to all these people. It was mostly, students, postdocs, and there were actually in this group there was only 5 regular staff, including myself at that time. Anyway, but even more important, the director of the NIST lab that controlled these basic experiments was Catherine Gebbe. She was the boss of both Bill and I, and I think we would both say she was a wonderful leader, and she was like she was like her little old grandmother. So, you know, she's a small lady, and but she was a tough administrator. And what she would say, and what Bill and I, you know, benefited from, is basically her philosophy was, you know, find good people, give them money, and let them go. So she never stepped down to try to manage what we were doing. So it was a great experience. So anyway, so we were both lucky to be, I think we're, you know, this is still a good place in the same way, but we were particularly lucky that we were one of the good people that she chose. Anyway, with that, I'll stop. Thank you.
Thank you, David, for a so nice presentation. I hope most of you follow. It's a field in expansion, right? And people are claiming to physicists to prove where we're going to get with the quantum computers and stuff. But now we can open for question, and I'm sure David will. Oh, by the way, David, he did not bring you the presents, but he's the one that financed the paçoquinhas outside. And I know that they did not let you with the paçoquinha inside, but it is waiting for you as you go out. And I ask, well, let's go for the question, and then we have some more surprises. I'm going to ask somebody to help with the other microphone so we can circulate. So we have two questions, and the present is the paçoquinha. Is a quantum paçoquinha? No, it is. I had a piece, and suddenly I didn't know where it was, and it was very strange, quantum food.
You got a customer over there.
Okay, but
first, thank you for the presentation. And I'm curious about, there's, in sense of perspective, there's any equivalent to Moore's law in the context of the qubits, like a perspective of how the number of qubits will grow in the networks?
I didn't understand the first part. You're asking if there's a connection between.
the Moore diagram.
Oh.
Is there any equivalent?
Oh, I see. The scaling.
If there's any equivalent in the case of qubits?
I mean, we hope that there's a scaling. We're going to be able to increase the number. For Moore's law, it was, I think the basic idea was, you know, it's not a law, of course, but the trend that was observed was the number of you know, transistors on a chip, miniature chip was doubling every year and a half. I forget the exact number, but so it wasn't a law, but it was a scaling. But I think that's, you know, in order for us to succeed, we're going to have to do the same thing. We're going to scale up much larger than the number of qubits I've talked about. We'll see, but anyway, yeah.
First of all, thank you for the presentation. It was amazing. And my question's a little more personal. I would like to know what was your correlation with this area of study in your early stages of university, and how was your evolution of interesting while your professional career?
Can you help me out? I don't quite understand the question. But can't hear. Oh, I see. Well, by accident, but so just a little bit of my background is when I went to graduate school, I worked for Norman Ramsey, who was one of the most famous atomic physicists of the 20th century. And this was at Harvard. And there I worked on things that were related to atomic clocks. I worked on masers, which are like lasers, but at microwave frequencies. But then I took a postdoc with a professor named Hans Stamos, who was at the University of Washington. And he was doing ion traps, but he was actually doing similar trapping things, but with electrons. And in fact, his most important projects were working on using the similar trapping techniques, but to measure the properties of electrons. And in fact, his major claim to fame, and he won a Nobel Prize, was that by measuring the magnetic moment of an electron, that is an electron, like other particles, it has one property it has is electron spin, but there's also a behaves like a little magnet. And the interesting thing about the electron is that the magnetic moment of the electron with quantum electrodynamics can be calculated with an imprecision of about a part in 10 to the 12. And in fact, he was able to measure actually measure the magnetic moment to that precision. And this is regarded as the most precise test of quantum electrodynamics that there is. So anyway. Oh, and then what about me? So that's how I got interested in ion traps, because I was working on electron traps. And then I went to NIST, and because I had interest in clocks and frequency standards, that's why that's kind of led to this first, and then later atomic clocks.
Professor Wineland, I want to know what are the advantages of quantum computing, and what could be wrong or dangers for humanity when it comes up?
Well, I think first of all, the main advantage is that I think in the long run there was this potential application for factoring, and I think that's going to go away. I mean, I think maybe I mentioned, but anyway, Peter Shor has said recently that now he doesn't think a quantum computer could crack the most advanced code. So, but I think to answer your question, I think the most important application is to simulate other quantum systems, and that's where the real application will be. And I'm sure there'll be people that will want to use quantum computers for various nefarious things, but something like that is always going to happen. I think we have to guard against things like that. But.
Can I ask the question, please?
First of all, thank you for the lecture. And my question is a bit more general, but with all of that in mind, why do we need to keep our quantum computers at such low temperatures?
Oh, low temperatures? Yeah. It's mainly, well, you can see we were, in this experiment, we were one thing we needed to control was the motion of ions. And in fact, we had to invoke the logic gates that I talked about. We had to cool the motion modes down to absolute zero. So that was the application there. And there's similar concerns with superconducting qubits. They don't have to be in the exact ground state, but temperature is, high temperature is a problem for them as well. It introduces gates or errors. So both these systems, you want very low temperature to freeze out, any other extraneous effects that you don't want to have to deal with.
Thank you, first. And correct me if I'm wrong. There's a difference between the two states of energy. And this affects somehow, some way, the superposition. The distance between this.
Oh, I see. That's a good question. But in fact, to a very high degree, even though we have this Coulomb coupling that makes these motional modes, it turns out just the numbers are such that the Coulomb coupling doesn't affect the qubits very much at all. That we have to account for it, but it's a very small effect. So it's a good question, but it turns out we don't have to worry about that so much.
Please, thank you for the lecture. It's a pleasure to be here. I would like to ask, it's related to the gross cash question. I couldn't understand what are the main differences of a quantum computer and a classical computer, physically speaking. So I couldn't understand what's this main part.
Well, yeah, I mean, it takes a while to explain it, but where the efficiency comes is to be able to work with superpositions. So, you're just, in a normal computer, it's, bit by bit interactions. But with a quantum computer, you can have a whole family of qubits that are interacting together. So it's kind of, that's a crude way of answering your question, but it's the fact that you scale up by having multiple interactions going on at once rather than bit by bit.
Okay, thank you.
Hello, thank you for your lecture. I was curious about metrology. How do scientists that work in this area plan to use this kind of research to expand the measuring beyond quantum limits? You said something about that in one of the...
Were we talking about metrology? Is
metrology.
That? Okay. Well, one way I'll do a cheap advertisement. I'm going to talk...
Maybe if you want to understand it, those ions seem to be very good for metrology in general.
You said that for the future, one of the prospects is to expand the measuring beyond quantum limits, right? So I was curious if how the scientists would do that.
How the...
Go beyond the shot noise limit.
Oh, I see, okay.
Go to very high precision.
Yeah, okay. Well, I'll give you maybe a better idea tomorrow, but one way to say it is if we talk about shot noise, when we measure the state of the qubit, early on I mentioned that we could tune to an optical transition that only coupled one level to an excited state, which would then emit radiation. We could scatter, we could do that measurement many times, millions of times before we would disturb the lower state of the qubit. So that's one way we got rid of, the shot noise effect. Is we do it averaging by scattering many photons, and we could suppress the shot noise that way. Yeah.
Hello. Firstly, thank you for the talk. And when you became a Nobel Prize winner, how did you feel?
Where? Who's talking? I can't. Wave your hand. Oh, sorry. Okay. So what was it?
What you feel when you became a Nobel Prize?
Well, pretty excited.
Were you expecting?
No, I mean, sure. A lot of physicists, I think a dream would be to win a Nobel Prize, but I think, I must admit I think a lot of people assume, you have a chance, but to give you an idea, I think, a sport with some physicists is to get up early in the morning so you can hear when they announce the Nobel Prizes. Well, anyway, they usually announce the Nobel Prizes at a little before noon in Stockholm, Sweden. And anyway, I think it was about just a little more 3 a.m. in Colorado, where I was at the time. So I was sound asleep, and in fact, my wife heard the phone. I wouldn't have woke. I would have slept through it. But anyway, so this guy was, it was the president or the head of the National or the Swedish Academy of Sciences, and he's the one who made, told us, and people like me. And so, anyway, I was, of course, it's like a dream, and for a while, but it was, in fact, what was interesting about this, a little side interesting, in Sweden, they just after they announce, or what they do is they just announce the winners, but then they give the calls to people like me, but the reporters many reporters are listening to this. So even on that call, when the person from the Academy of Sciences in Sweden was calling, I could hear the clicks on the phone, from reporters trying to get in for a quick interview, and so actually the person from the academy was very polite and, explained how things would kind of go for the next couple of weeks. But anyway, so after he signed off, the phone immediately rang, and I said, well, I'll take a call. And it was actually a reporter from Brazil. And, all the reporters knew that we'd get lots of calls. And so he just, we weren't on the phone for more than a minute, but he asked a few questions. And then, the phone, on that call, I could hear a bunch of clicks, So I answered a few more calls, but then it was clear I would just be swamped with calls. So this was about 5 in the morning, and I told my wife, I'm going to go to work. And so, because what happened was I knew that at work they would have a press conference early in the morning that would take care of most of the reporters from around the world. But what was one funny thing which I like to tell was that, my work phone, had an answering machine, so it was, it was getting lots of calls stored in it. And so by the end of the day, there were several hundred messages I had on my phone, and I eventually answered all of them. But anyway, I didn't that day. And so I just saw that there was many calls. And when I was ready to leave my office, the phone rang, and I thought, well, I'll just take this one call. And the guy says, is this David Wineland? I said, yes. And he said, this is Air Force One. It's the U.S. President's airplane. And this was President Obama. He was on his airplane and to congratulate me. So it's the one call that I took was probably the most important one. Anyway.
I have a book that David gave to me. That was about 15, 20 years ago. And he wrote, there was a book about quantum science and progress. And there was a chapter about his work. And then he wrote to me, to Vanderlei, that is how close to fame I will get. So I'm going to get the book, and now we're going to put the picture and say that not always those statements is true.
This was before the prize, right? Yeah, okay. Yeah.
We have a few, let's get two more questions, because then we're going to do like yesterday. David and Bill is here too. They're going to stay here and you can approach and take. And there is a secret surprise here that I want to give. We're going to have time for that. So there is one question. You are helped to do it.
Okay, thank you, Professor, for the excellent presentation. The question is open-ended, really, but I was beginning to wonder, as someone that's working with network science right now, I saw a fully connected graph there, and I was like, what will be the state of art between network science and quantum computing right now? Would you care to explain, talk a little bit more about that?
I must admit, the sound is here. I couldn't understand very well, but
I think she is asking about the quantum computer and natural science.
No, network science.
Network?
Network science.
I see.
Yeah,
So
the interface between.
Right? Oh, yeah, well, I think, certainly network scientists are very interested in this because it would improve the efficiency of networking for sure. And so, I don't know the details particularly how they're interested, but it's clear that things would scale up much better in networking. Yeah.
And that would also imply in the way we would deal with communications in the future, probably, right? The way that my son said.
We can think about new communications way in the future.
Well, that's right. There's certainly you can. They certainly can think of completely secure communication using the quantum ideas, because you can tell when someone is interfering with the system. So, yeah.
Thank you.
The hackers may not do so well with quantum computation.
Hello. First of all, thank you for everything. It's been a pleasure and an honor to be here and just listen to you guys, and it gives me shimmer. And I'd like to ask why physics, and similarly, you ask. Oh, I forgot about the word, but own thing. Why Bill chose physics, and I like to ask you too. Why physics?
Why I chose physics?
You asked Bill yesterday. What was he's asking?
Oh, yeah, yeah. Okay. Well, my story is not very profound. As a young kid, I liked mathematics, and I also liked mechanical things since I was a kid. And so, I saw how mathematics could help describe mechanical systems and other things. And so and because I like mathematics, I was immediately drawn to quantum mechanics. So it just kind of grew from there. But I didn't, certainly when I was in high school, I didn't think I was going to be a quantum scientist particularly. But,
And David is a very good biker. In Boulder, high altitude, it's not easy. Okay, so I know that there are many other people for questions, but we're not going to leave. So I think it's better if you approach and, like yesterday, David can answer the questions. I told you about the quantum paçoquinha, which is wonderful, you should try. But I asked Bill to bring his Nobel medal. And I think many years ago you brought. I remember people putting it everywhere, took pictures. But then this time he brought some equivalent. So we have here 4 medal, which is very tasty because inside there is chocolate. And it comes from the same place where the Nobel real medal comes, right, Bill, from Stockholm?
Well, it comes from the Nobel Museum.
Nobel Museum. So, what are we going to do? There are 4. I'm going to ask David to sign 2 and Bill to sign 2. And we're going to give it to one student female, one student male. And we're going to have to make a lottery, right? Because you cannot throw. So I'm going to give you the 2 medals that will be presented to the woman in science here in your institute, to Christina. And she'll take care to go to the graduate and undergraduate and make a lottery, and then they communicate to you and you get. The same with the 2 students, okay? Of course, I don't know how to do different than 2 by 2. And you see, they put the picture of Catherine, right?
Catherine,
which
yeah.
was, I remember, she was very short. And she was the manager of NIST laboratory. Because you see, it's not easy to do science when you want to do something. What?
What's the problem with being short?
No, no problem. She was a high concentration of energy. Because you see, 30 years ago, doing this kind of science, promising to advance knowledge, was not so easy. And you need always some people that believe what you want to do to say, go ahead. And I believe that she was one for NIST, right? Either in the atomic or the ion group. And that's why I said we divide in 2, right? 2 for the boys, 2 for the girls, or whatever is the mixture. Today is superposition, and we all respect them, that's fine. Okay, so I'm going to ask David to sign 2.
Okay.
And Bill, can you just sign here? And the good thing about this one is soft enough they can sign. It would be nice to put your name, but we're going to make a lottery.
Yeah,
Christina, you
probably.
agree?
But you're not going to give them away right now, right?
No, we're not going to give away right now.
We maybe a better marker. Yeah.
Oh, we're going to use a sharp pen. It will be forever. Okay. But this will be done.
We promise we won't eat them, though, in the meantime.
Well, I hope you don't eat them.
I think they're old enough that they wouldn't be very good to eat.
And then you keep it. Right? Okay. So before we disassembled the auditorium so you can come and ask local questions, I want to thank you all for coming. As I told you, we had to leave for the end. The idea was to do in the week of physics, but the week of physics in our institute coincided with everything else in the world. It's very hard to bring people, so they accept to come now and give these wonderful lectures. And I thank you all for coming. I hope you are motivated for
and
this
I think
area.
Bill want to, and I want to thank the audience for coming.
The director now should be here, and I think they want to say a few words, and we all happy.
So thank you very much, Vanderlei. I just want to thank you once more for being with us and giving us the privilege of talking to so many young people. And I see this audience, it's a wonderful audience, the best audience, the biggest and best audience that we ever had in this auditorium. And thank you all. Muito obrigado.